Hey guys, this is Shayan and today I'll be talking about Centroid. Well, Centroid is a very important and useful approach when you want to solve problems on trees. Before comprehending what is Centroid, you need to be familiar with trees, how to keep them, and a little bit about divide and conquer. So if you're not familiar with them yet, maybe it's better if you start learning them first. Maybe by the time that you're watching this video, I have also added videos about these topics and you can check the description of this video to see the links of those videos. Today, I'll be solve one problem about Centroid at the end of this video, which is Ciel the Commander 321C from Codeforces. Also, I introduced 4 other problems to you, like distance in tree. This problem can be solved using simpler approaches because its constraints are low, but I most of the time tell my students to solve it using Centroid as well in order to just train for Centroid. Another problem is Xenia and tree from Codeforces, and Creto Memeland from CodeChef, and closed vertices from Codeforces. These last 2 problems use data structures like segment tree alongside Centroid. So you need to be familiar with these data structures as well in order to solve these 2 last problems. Okay, so now let's discuss what is Centroid. Well, Centroid is a vertex in tree such that if you remove this vertex, all the remaining connected components will have at most n half vertices. So it means that if you remove this vertex from your tree, all the remaining components will have at most n half vertices. So why is that important? You know, if you are familiar with divide and conquer, you know that we always try to find some smaller subproblems and solve them, and by dividing them and solving those smaller subproblems, we will try to solve the whole problem. Here, Centroid is somewhat like the middle of the tree. It's like a vertex that's, by removing it, all our subproblems will have at most n half of the vertices. For instance, if you are familiar with the simplest problem, binary search, you know that why n half is good, because when you always divide your n by 2, you know that these divisions will last at most log of n times, and this gives you a good time complexity. So this is the definition of Centroid. Now a question arises that why a Centroid exists and how can we find it? How can we find it? And also there are other questions like how many Centroids can we have in a tree at most? And are there any other definitions for Centroid? I will talk about them in another video because I don't want to make this video very long. So I will talk about them in another video that I will link it to this video. But let's talk first about why a Centroid exists and how we can find it. Well, I tell you that an algorithm that using this algorithm you can find a Centroid. And when you can find it, it is also a proof that it exists. Because if you can find it, then you can show that this vertex is Centroid. So it exists. So let's talk about how can we find a Centroid. Well, in order to find Centroid, you can start from your roots. You can set any arbitrary vertex as your root. For example, you can start from vertex 1. And you can check its children. Assume that you set 1 as the root of your tree, and these are its children. If the size of all of them is at most n half, then vertex 1 is a Centroid, and you're done. because if you remove it, all the remaining components will have at most n half vertices. So you're done this way. But if it's not, assume that you have at least one child that its size is greater than n half. Well, first off, I want to say that there will be exactly one child such that it's the number of vertices in it is greater than n half. Because if you have two of them, then the total number of vertices is more than n, which is a contradiction, because we said that we have n vertices. So what we can do is we go from this vertex to this new vertex here. And again, in this vertex, we can check its children. If there are two possibilities. If all of its children are n half, then I will argue that this vertex is centroid. We will see why. Otherwise, if it did not happen, again, there is one child such that the size of the number of vertices in here is greater than n half. Then I can go to that vertex, and so on. So until I have at least one child such that the size of the subtree of that vertex is greater than n half, I will go to that vertex. I will stop at some point. I argue that that vertex is a centroid. So assume that I stopped here. I started from my roots and I came to vertex V, and here I stopped. Here all my children have size at most n half. I want to argue that this vertex is a centroid. And definitely we will stop somewhere, because our height is, each time that we go down, our height will be increased by 1. And it cannot increase infinitely. So we will stop at some point. So if we remove V, we know that all these components, the size of them is at most n half. And also these components, which is all the vertices outside the subtree of V, I want to argue that this component will also have at most n half vertices. Why? Because we know that the number of vertices in the subtree of V was greater than n half. That's why we came to V. Otherwise, we wouldn't even come to V. We said that we always go to a vertex if and only if the size of its subtree is greater than n half. So if we came here, we know that the size of the subtree is greater than n half. And we stop in here. So the size of this subtree is greater than n half, and the number of vertices outside of its subtree is definitely less than n half. So it's also less than or equal to n half. Therefore, V will be our centroid. So this can be our algorithm to find the centroid. And since we found the centroid, then we can be sure that it exists. It's only enough for you to start from the roots and go down until the point that you stop. And there it is. There's your centroid. So this is how you can find your centroids. Now I want to discuss that how can you use this to solve a problem. And I want to solve the first problem that I introduced to you and implement it and get accept from this problem with you. The point is, when you find your centroids, then the fact that all these remaining components have at most n half vertices, it's very useful. It really helps you to find good time complexities by knowing this. For instance, if we read the first problem, Ciel the Commander, this problem says this. This problem says that assume that you have a tree of size n and n is up to 10 to the power of 5. We want to put a letter on each vertex. Letters can be from A to Z, and all the letters should be capital. And there is one constraint, and this constraint is that if you put same letter on two vertices, for example, put letter D on these two vertices, then in the paths between these two vertices, there should be at least one letter with higher priority. So there should be at least one A or B or C or D in the paths between these two vertices. So there should be at least one, for example, B in here. Okay, so the only constraint is that if you have two vertices such that their character is same, in the paths between them there should be one vertex with a letter with higher probability, with higher priority. Okay, how can we solve this problem? Well, I want to use Centroid in order to solve this problem, and I say this. Let's find Centroid at first. I want to make a statement. I want to make a statement that if I have a tree of size n, then by using log of n plus 1 letters, I can solve the problem. So the only thing I'm saying is that if I have n vertices, I will always be able to solve the problem if I only have log of n plus 1 vertices. And this plus 1 is just because, for example, if you have only one vertex, then log of n is 1. So, then n is 1 and log of n is 0. Therefore, you have 0 letters. So I add 1 to it so that I'll be sure that, for example, when it is 1, I will have 1 letter. And for example, when it is 2, I will have 2 letters. Okay, so I need this additional 1 as well. So this is my statement, that if I have n vertices, by using log of n plus 1 letters, I can always solve the problem. How do I prove it, and how do I solve this problem? I just say that I find the centroid and I put the letter with the highest priority there. For example, at the beginning, it is letter A. And I know that in all these components, we will have n half vertices at most. So assume that I had log of n plus 1 different characters in the beginning. So now, in each component, I know that I have at most n half vertices, and now I do not use A anymore. So now I have log of n characters. I just put A in the centroid, and I do not use it in these connected components that I make after removing this vertex. So I will have log of n vertices in here. It's just enough to say that this is equal to log of n half plus 1. So I still have n half vertices and log of n half plus 1 letters. And by using induction, I can say that recursively, I can solve this problem by using letters from B to the last letter that I can use. And then after doing this, I know that inside of each of these components, the problem is solved. And if I choose two vertices from two different components, I know that one side of it cannot be this vertex, because this vertex is A and no other vertex is A. And if these two vertices are from two different components, I know that there is an A between them. So therefore, I'm sure that in the path between them, there will be at least one vertex with a higher priority. Therefore, this way, I'm sure that for all the pair of vertices with the same characters on them, in the path between them, there will be at least one vertex with a higher priority. So again, inside of each of these connected components, I find the centroid of that connected component, that subtree. I'm just solving the problem recursively. So I can just, for each of these connected components, find the centroid of them and put B on them and solve the remaining problem using letters C to the last letter that we have. So this way we can solve the problem, and it will have all the constraints, it will have all the requirements that it needs to have. So let's now implement this and get accept from this problem. I usually use VIM to code, but here, because I believe that it might be simpler for you to see it, I will use just Atom. So let's start it. Well, first I need to also include vectors in order to keep the edges. I just define const int of n as 1 if 5 plus 20 because n is at most 1 if 5. And I should also define the g of n, which is the graph, which is the edge of the graph g. And also char of res of n, which is the results. Okay, so let's start. Well, first I get the inputs. I just use functions for getting the input here. You know, in competitive programming, you don't need to code like this. I myself do not code like this when I'm in a contest. But because here I believe that this way it would be easier for you to comprehend what is going on, I will implement it like this. So first I will get the inputs. It is just I should get n and I should get all the edges. And I use zero-based indexing. So I say u minus minus and v minus minus, g of u dot pushback v and g of v dot pushback u. And we're done with the inputs. We should also have a function for outputs. And in our output, it's just enough to say that we have a 4 on all the n vertices, and we should print the result of vertex I and an endel in the end of it. Okay, so now we want to, in the middle of input and output, we want to solve the problem. Well, when we want to implement such an approach, well, the best thing to do is to always pass one vertex of the connected component that you want to solve. For example, you are here and you want to solve this connected component. The best approach is to pass one of the vertices, one arbitrary vertex of this connected component, and then start a DFS and find all of the vertices around it, all of the vertices in these connected components. And you can also make all of the vertices which you have processed them, you can make them dead. So you can say that, for example, if this is vertex v, you can say dead of v equal to, let's call it c, as it stands for centroid, because this is the centroid. So you can make dead of c equal to true, so that you are sure that this vertex is dead. This is processed, so this is not part of this connected component. So you pass only one vertex to that connected component, and inside that you will run a DFS and find all of those vertices. So what I'm gonna do is just pass a vertex, which is vertex 0. This is an arbitrary vertex. So the first vertex we are going to run a DFS, and we will see all of the nodes, because at the beginning no vertex is dead. And we also pass the current character, which is initially a, so because we start from character a. But when we process this vertex and we will go and solve the rest of components, we should pass b to them, because a is done. Now we should start from b for those components. Okay, let's start doing it. So I should say void.solve int of v and char of current char. And first, I just run a pre-DFS in order to find the sizes of the subtrees. I need that to find my centroid. So I just define size of n and a boolean of dead that I'm gonna need to kill a vertex and do not use it. And as I said, we have to define dead of n, because it's when we want to remove a vertex and solve the remaining connected components. And now we should run a pre-DFS. Int of v, int of parent equal to -1. So I will have a 4 on all the adjacent vertices if u was not equal, if u was equal to parent or it was dead. I will continue because I should not go to this vertex. Well, u equal to par is obvious, it's part of DFS, and if it is dead of u, it is again obvious because we removed that vertex and it is not part of this connected component. Otherwise, we should just pre-DFS of u and v. And in the beginning, we should say size of v is 1. And here we say that size of v plus equal to size of u. Okay. And after this, we should find centroid. So we say that cent is equal to find centroid of v. And we also pass size of v as well, because it is the number of vertices that we have in this connected component. So I pass the number of vertices in this connected component to know that if the size of the subtree of some vertex is more than the half of it or not. So I just here say that int of find centroid, int of num, which is the number of vertices, and int of v, and int of par equal to -1. So I can just say that for int of u on g of v, I can say that if u was not equal to par and then it wasn't dead, and then 2 times size of u was greater than num, then I should return find centroid of num, u, and v. I should go to that vertex and find the centroid from that vertex. Otherwise, this vertex itself is our centroid because none of its children have that situation, and this vertex has this situation that we came here. Therefore, this vertex is our centroid. So this is our centroid, and by given any tree, we can find the centroid like this. We can always find the centroid. So now it's only enough to say that rest of centroid is equal to current char, and dead of centroid is true. And we should have a 4 on the adjacent vertices. And I can say that if it wasn't dead, I should not solve those connected components that I show them with this vertex u. Okay, so I have this vertex u, I pass them to the solve function, and then from there I run a DFS and find all the vertices in this connected component. So I just say solve of u and current char +1, because now I should start from the next character. And by doing this, and sorry, it's not g of v, it's g of centroid. So by doing this, we can just find the answer for these connected components recursively and solve the whole problem. Okay, so it seems that we are done now. So let's see if it works. Okay, I forgot to define u and v. Okay, so let's run the tests. The first one is answered correctly, and the second one is also answered correctly. It is working as we wanted. It's made the centroid A, and then in the remaining connected components, in these two connected components, it made the centroid B, and then in the remaining connected components, it did the same thing. So it is doing good. So it's just enough to submit it, and let's see if it gets accepted or not. Okay, it is getting it got accepted, and this is how we can implement Centroid and solve a problem like this. Okay, so we saw how can we solve such a problem using Centroid and how we can implement Centroid. As I said, there are also harder problems using Centroid. If you want me, I can solve them as well and make a video for that. Also, if you know other problems about Centroid, it would be great if you put them in the comments below, and I can also make a video for them as well, and other people can also see those links and solve those problems. If you had any question about Centroid, you can ask that from me in the comments below, and I will try to answer them one by one. I really try to answer all of them. And if you want, I'm trying to make videos as much as possible in order to help you. And if there's any specific topic that you want me to talk about that one first, tell me, and I will try to make a video about those topics. And as I said, I have another video about Centroid that I will talk about additional things. I will tell that how many Centroids can we have in a tree, and another definition for Centroids, and also a very, very interesting proof for the existence of Centroid. And I put that above, and you can see that video as well in order to get familiar with those things as well. I'm trying to make videos as much as possible, so if you like this work and you want me to continue doing these things, you can support me and like this video and subscribe to my channel. Thank you very much.